Again, thank you for joining us for this academic lectures this afternoon. The second presentation would be entitled Small Object Detection, Tiny Targets, Big Problems. In our lab, we do a lot of object detection projects. We have a lot of image classification as well, but object detection, specifically small object detection, is one of the important problems in the object detection field. So in this talk entitled Small Object Detection, Tiny Targets, Big Problems, it will be discussed by one of our, again, BSMSCS student researchers. Let me read the abstract for you. So small object detection is a specialized challenge in computer vision where objects occupy only a tiny portion of the image, making them difficult to detect and classify. As I've mentioned, this is a very important problem in object detection, primarily because there are a lot of applications wherein we need to detect tiny objects in our data. This lecture explores how small and densely packed objects are defined and categorized, the visual and technical limitations of detecting them, and why many conventional detection approaches fall short. It also introduces state-of-the-art solutions, highlighting their impact on real-world tasks. The outline of the lecture is as follows. So we are going to discuss the background of small object detection, some challenges in detecting small objects, techniques and solutions, and we're also going to cover applications of small object detection. Let me introduce the speaker for this afternoon. This lecture will be delivered by Rafael Suboyap. He's currently a third-year computer science student at De La Salle University under the BSMSCS Honors Program. He's also a tutor with the Peer Tutor Society, or PTS, of De La Salle University, and a member of our research center, the Center for Computational Imaging and Visual Innovations. His current research focuses on the optimization of deep learning models, trying to count small objects, in particular, mosquito egg detection, as a tool for vector surveillance and public health. So I will now turn over the floor to Rafael. Rafael, you may share your screen and start your presentation.
Okay. Good day to everyone. My name is Rafael Yap, and this is my academic lecture titled Small Object Detection, Tiny Targets, Big Problems. So this talk will focus on applications of small object detection, the background of it, challenges, and solutions we have right now. Okay, so small object detection, or SOD, it isn't just a smaller version of the broader object detection task. It's a specialized subfield with its own unique set of challenges and also its own importance. You might think, if the object is small, how important can it be? But in many real-world scenarios, these small objects are actually the most critical to detect. Imagine you're driving down a highway. Being able to spot a tiny road sign far in the distance can determine whether a vehicle makes the right turn or not. If you have medical imaging, like what Christian showed a while ago, detecting like a small tumor can mean catching a disease early or missing it entirely. And in security contexts, like drone surveillance, spotting a tiny flying object could mean detecting a threat before it escalates. So despite their limited pixel size, small objects often carry enormous significance. Now we start with the definitions. So when we talk about small objects in computer vision, we're not just speaking subjectively. Benchmark datasets like MS COCO actually define small objects with areas less than 32 by 32 pixels, or just around over 1,000 pixels in total. And in more specialized domains like UAV or satellite imagery, so their datasets often classify small objects as objects with less than 20 by 20 pixels. So here I have an image of a countertop, and this is going to be more object segmentation, but I just wanted to see show how a good small object detection model would detect objects here. So here we show that it's supposed to highlight even stuff like the forks or the cups that are quite small in this context, then it's supposed to be able to classify them properly. Next definition we have is relative size criteria. So defining what counts as a small object doesn't always depend on its pixels dimensions alone. Sometimes some papers will define them using their relative size, how large an object appears compared to the image it is in. This can provide a much more realistic and context-aware metric. For example, in TT100K, the image here is from that. It's like a data set filled with streets and stop signs. Since their image is higher quality, like higher resolution, they define small objects as objects with less than 30 by 30 pixels in their images. So commonly also, objects are less than 1.5% of the total image area. This issue becomes even more pronounced in like ultra high resolution domains like satellite or aerial imaging, where the image can reach gigapixel scales. So there, if you just had the normal relative the normal definition we had, the pixel-based definition, it wouldn't work that well because since it's so high resolution, even a 50 by 50 or 100 by 100 pixel object, something that would seem large in typical computer vision datasets, is still very small compared to the overall frame. Yet these objects are critically important too, like a stranded boat, like I'll show later, or a military vehicle, or a deceased spot on a crop field. Okay, so we see that if it was a good model, it would be able to detect even these very tiny stop signs far away. Now we'll talk about the applications. So the first application of small object detection would be something like maritime surveillance. So detecting tiny vessels, life rafts, or floating debris across vast ocean surfaces. These are very critical for safety, search and rescue, and coastal security. Okay, so we have this high resolution image here. We're trying to detect all the boats. What if we used a normal object detection model? Okay, let's try to detect it. If we had a theoretical normal object model and it would detect only these items, wouldn't that be hard? In vast ocean areas, missing a small raft or a boat can be life-threatening. But it's because these models are designed to detect objects generally. So these objects at the back seem hard to detect. So if we had a good model for small object detection, this is what it would look like. So many rescue missions rely on aerial or satellite imagery, like what we see here, where objects are very, very tiny. Surveillance systems must detect these with like minimal false positives, and there's stuff like waves or reflections that can make it even harder. So small object detection that is very optimized can enable early warnings, efficient search zones, or real-time coastal monitoring. Next application is defect detection. So minute cracks, scratches, or wear patterns on metal or glass surfaces. This is essential in manufacturing quality control and predictive maintenance. So even the smallest imperfection can lead to failure in aerospace or electronics. Okay, we see here, this is like the partial image defects. It isn't that hard to notice that there's a defect here. But imagine if it was this full-scale image. That must be very hard because if you had a group of people and there was a pipeline of these different parts and you're trying to force them to check each defect individually, that would be very hard even for a person. So that's why models would struggle. So these are often done using industrial cameras and automation pipelines. So small object detection here is what allows that to happen. And the other problem here in defect detection is these detection models must distinguish actual true defects from harmless marks or dust. The next application we have is agricultural monitoring. So in agriculture, small object detection plays an increasingly important role in stuff like precision farming or large-scale crop monitoring. For example, farmers and researchers can use small object detection models to detect individual pests, or early signs of disease, often before symptoms are even visible to the naked eye. Catching these signals early can be crucial for preventing outbreaks and minimizing crop loss. It's also used for automated fruit counting, or here, automated palm tree counting, which provides reliable yield estimation and supports better harvest planning. This is particularly useful for large plantations like we see here, because imagine counting this manually. So when using drone or satellite imagery, tiny visual differences such as color shifts, there's texture changes, or patterns can reveal signs of nutrient deficiency too. So traditional object detectors often miss these. So this is where small object detection adds real value. Okay, we see here, a good small object model would look like this, where it detects all of them, and if we zoom in, it was able to count them properly. So now we talked about the background and the applications. Let's talk on if small object detection is an actual problem. To show that it is, let me show the problem in numbers. This chart shows the average precision for small, medium, and large objects, AP small, AP medium, and AP large, across popular detectors like YOLO V4, SSD, and RetinaNet. As you can see, every model struggles with small objects. Even the best here, YOLO V4, just gets a 24.3% average precision on small objects, while it gets double that for large ones. SSD here drops to 10.6, and refined that even smaller with 10.0. So these performance gaps are not minor. They're telling us that our current models fundamentally struggle when object scale decreases. As we see here, from large images to small, there is an average drop of 25 to 30%. So this is why small object detection needs its own tailored strategies compared to just normal object detection. Okay, let's talk about now why it's a problem. The key challenges we have in small object detection compared to normal object detection. Okay, let's begin our discussion of key challenges with a visual analogy. So if you guys played Minecraft before or any game with draw distance settings, you'll recognize this. At low render distances, you can't really see what's far away. Distant objects fade into the fog or just don't load. We can't really see what's here at the back. So this is very similar to what object detection models deal with. If an object is too small or too far away, it essentially becomes invisible to the network. The back here is also invisible to us. So just like how the world becomes clearer as we increase render distance, improving our model's ability to detect distant, tiny targets, this requires specialized techniques. Okay, let's increase the render distance. More objects become visible. We can see that there was actually a river here, but we still can't see the fine details. We might see here vague shapes. We can see a bit of shapes here in the river, but we can't really distinguish what they are. So as a model, you're gonna be able to detect that something is there, but you can still struggle with correctly classifying it or localizing it. You can see that there's an object far away, but do you know if it's like a stop sign, if it's a person, if it's a mailbox or a car? Okay, let's turn up the render distance one last time. At maximum render distance, we get clarity. We didn't see this a while ago, but now we can see that there was kelp here, and distant objects appear with greater structure and more context, less invisible objects at the back. This is the goal of small object detection. We have to train models that maintain this clarity across a range of scales, especially at the small and distant end of the spectrum. But we'll see with the rest of the challenges, it's not really an easy task. So our ability to see distant objects depends on clarity, size, and the visibility limits. So connecting this, we talk about our first challenge, low appearance quality. Small objects often contain very few pixels, like what we said in the definitions, meaning there's not enough detail to capture their unique characteristics. Even worse, when they're very far away. Those few pixels may be blurred or distorted by environmental factors like fog, glare, or rain. This makes it extremely difficult for networks to extract meaningful features because those features aren't like really present. Okay, now we use the same image as we did a while ago. Then let's show the hard objects. See, from this scale, it's barely distinguishable from water. Some of them even blend with the water. Now we zoom in even more. We see that there's indistinct edges and low contrast in these images. They just look like blobs. Even in a high resolution satellite image, these boats appear as like low detailed blobs. Their visual features, which are barely there, their edges, texture, and shape, they're not really seen. So this isn't a problem of just a sensor, it's the reality of scale. So small objects don't get more detail even in clearer images. If you zoom in, you'd think you'd see stuff like the windows of the boat, the hull, the ropes, the outlines, even the shadows maybe. But what we really get is this handful of pixels only. It's barely separated from the sea too. So this lack of visual cues makes it hard for even a human to identify what this is, let alone a model. Next problem is in training data. In the MS COCO dataset, one of the most widely used, small objects make up just 1.2% of the data. That's a huge imbalance. Models trained on this skewed data distribution naturally get better at detecting what they see more often. So they see more often large objects, medium objects, so they're gonna underperform on the smaller objects. It's like when we're studying for a test, we usually perform well on the topics we study the most. Sometimes these topics have the most questions, so of course we'd study them too. But for the chapters or the parts of the test with the parts we just skimmed through, we're not going to perform as well. So if we only focus on some specific lessons, we disregard others. We'll do really well for the most part on the lessons we studied, but the ones we skimmed through, it's just going to be not as good. It's the same for models. Models learn what they see the most. So if we want models to detect small objects effectively, we have to either have more balanced data sets or techniques to compensate for the skew, because sometimes you can't really have balanced data sets all the time. Next challenge in small object detection is in scale variation. So what you're seeing here is a sequence of drone images taken from different altitudes. Here we gradually zoom in on the same scene, but the object class doesn't change. It's just cars on a highway. But notice how radically their size and their appearance change depending on the drone's height and angle. To show this, let's choose a car. Okay, it's very small. You can barely see it. Let's go to the next image as we get closer. Still really small, but at least it's like a colored dot. Here, the next image, it's just a bigger colored dot. But when we get closer a bit more to the next image, it's still a car, but we see it better now. Then the next image, it's clearly distinguishable from like the road and the other cars. Then in the last image, so yeah, so from indistinct to clearly identifiable, but it's the same object class. It looks very different though. In the first frames, the cars are barely colored dots. In the last frames, they're full objects. So they have very visible structure, and the extreme variation we show here happens all the time in real world scenarios, whether from moving aerial cameras, dynamic zoom in phones, or even fixed surveillance cameras, because those have different depths of field. So the problem is most object detectors are not inherently scale aware. They tend to perform best on a limited range of object sizes. So when scale changes too much, especially within a single scene, the network's behavior can become inconsistent. It's also the angling. Look, here it's more horizontal, then the different patterns of it being more diagonal and stuff. This can mess up a network really badly. So there's going to be anchor box mismatches. The detector might not have the right shapes for tiny versions of an object, and like the angle can mess it up too. So it fails to generate good bounding boxes. There's also a loss of generalization. So the model learns to associate an object with certain patterns and scale. So if this is what the model is trained to, how is it going to detect a car that looks like this? So ultimately, this means small objects are easily missed or inaccurately predicted, even when they're critical to the scene. So techniques that can handle multi-scale representations, which we'll talk about later, or adapt to continuous size shifts are crucial for making small object detection viable in these type of real-world conditions, like traffic surveillance, aerial mapping, or what we showed a while ago, maritime surveillance. The last problem we'll talk about is in the networks itself, the feature learning limitations. So let's talk about what happens inside the network. In many deep learning architectures, features are progressively downsampled. So that's useful for making computations more efficient, but it comes at a cost. Fine-grained details get lost. And for small objects, those details are often all we have because we barely have any pixels. So on top of that, the signal to noise ratio becomes very low. A small object can easily blend into a noisy or clustered background, leading to missed detections or false positives. So here, we see that only the strongest activation from each region is kept. So imagine if one of these small boxes had details for small objects, it just gets lost. After all those key challenges, let's now talk about the techniques and solutions we have, or what we can do to improve object detectors right now. First is multi-scale feature fusion. So to address the problem of scale variation, the problem we talked about before, one of the most influential techniques is the feature pyramid network, or the FPN. So the core idea is to leverage CNN's natural pyramid structure here. So each layer captures features at a different scale. Then let's talk about each part first. So we have a standard backbone network. Here's the bottom-up pathway. So it has convolutional layers. From here, the top part is the lower resolution. Here is the higher resolution. This part is the encoder part of the network. This extracts features at multiple levels. Next, we have the connection itself. So these connect the bottom-up and top-down features. So these try to preserve spatial details at the same resolution. Next is the Next is the top-down pathway. This is when it upsamples. So it tries to merge the feature maps to enrich lower levels. So FPN has these top-down pathway where the higher level features are upsampled and merged with lower level features. So this fusion tries to retain the spatial detail and the semantic richness. So the result is a set of pyramid levels here that can be used to detect objects at multiple scales, especially small ones that would have been otherwise lost in these deeper layers. So, okay, FPNs work, but recently they haven't been the best for small objects because you still lose some information. That's where Bi-FPN comes to play, or bidirectional feature pyramid networks. So here, these are used in models like efficient depth. So Bi-FPN builds on FPN by making the fusion more flexible. So it adds bottom-up connections here also. So now information flows both top-down and bottom-up. Second, it also introduces learnable weights for each input to a fusion node. Then this allows the model to learn which feature levels are more important. So let's talk about each part. Okay, so we have the feature maps again, where the lower levels contain fine details. These are the details good for small objects. Then there's the direct connection layer. So these are the orange layers. We'll talk about them. We'll talk about this first, actually, the bidirectional cross-scale fusion. So Bi-FPN enables each node to take in multiple inputs, as we see here. Each output node takes in multiple inputs from either a lower layer or a higher layer, and it has learned it combines them into a weighted manner. It has learned weights to decide how much each input contributes. So the arrows here indicate how features flow in both directions. For example, here, like a mid-level node might get information from a lower level and from a higher resolution semantic layer. So the model will learn how to weigh them, and this kind of design makes Bi-FPN strong at detecting small objects because it requires the right balance of detail and abstraction. The orange arrows here are made to prevent small objects from being lost in the process. This prevents information loss during up and down sampling because this connects it from the initial input to each of the iterations of the output nodes. Because for the calculations, we're just repeating them. So to make sure none of these information gets lost during the process, we still connect them to each of these output nodes for each calculation. So yeah, direct feature fusion from initial input to every iterative output node. Here is just a zoomed in version of what we saw before. So it shows here that the P tree out of here gets information from features from P2, a lower layer, and from a higher layer. And it also shows the direct connection layer we were talking about, where from the initial input, we still get information. Next technique is tiling. So tiling is another effective technique for detecting small objects, especially if you have very high resolution images. So here we have an image of a busy intersection. By processing the image at once, maybe small objects like the distant cars may be missed due to insufficient pixel resolution. So the model is looking at the whole frame. But if you divide the image into smaller overlapping tiles, like what we'll see later, and we analyze each one, we effectively zoom in. Let's show it here. So this is the first partition of the image, okay? So it gets easier because the model is basically detecting in basically making it into separate images, and it's basically zooming in here because this is a smaller frame. It gets easier to detect these cars. So we'll see here, now it detects the middle. Then if we zoom in, look how easier it is. It's a lot easier to see these cars compared to if you just looked at this whole image. So yeah, we're basically zooming in. This makes it easier to detect them. So as the animation shows, each tile gets a turn at being analyzed, then the detections at the end are merged together. So that's how tiling works. But one caveat of this is since you're basically detecting in multiple images, it's more computationally expensive and it takes more time. So one modern implementation of this is SAHI, or slicing aided hyperinference. It uses heuristics to determine which regions to zoom in on, making it both faster and more accurate than just naive tiling. It's also useful for detecting small or dense objects in large images like aerial or street view shots. So SAHI keeps the context in mind while slicing. It ensures that detections are from different patches are harmonized and make sure that no object is detected multiple times or missed altogether. So this is from SAHI's GitHub. They show that a comparison of using a base YOLO model on an image compared to combining it with SAHI. We can see that the smaller, farther cars are detected by SAHI plus the YOLO model compared to just the YOLO by itself. The best part of SAHI is very easy to use also. It's a tiling pipeline, so it's already fine-tuned, so it integrates with any detection model. The last technique I'll be talking about is data augmentation. So the common image augmentation techniques like rotation, scaling, translation, flipping, and cropping, they are still used in small object detection. But now we'll talk more about advanced augmentation techniques because there's class imbalance and low data variability in most small object datasets. So we synthetically modify the input data. We can increase the variety and number of small objects in the model sees. The first one we'll talk about is the value-guided adaptive data augmentation approach. So this increases the focus on small objects during training. It works by selectively pasting here the small object instances into various background scenes. This targeted augmentation technique can counteract the class imbalance where large objects dominate training data. It floods the data set with more small examples. So this encourages the model to learn their features better and prevent underfitting. So we see here the objects bounded by the red box are just pasted into normal images and they have their own weights. The next two, the first one is mix up and the next one is cut mix. So these are also popular right now in small object detection. They're originally developed to improve generalization. In mix up, there's two images and they're blended together like we see here. And their labels are also combined together. While cut mix, it cuts a patch from two images and it pastes it into another. So for small object detection, these techniques introduce diversity too. So small objects get mixed into unusual contexts, so forcing the models to generalize better, especially when there's like training data is limited. So this kind of augmentation helps prevent overfitting and improves robustness. It shows that you kind of have to have really unique solutions to some of the problems that small object detection has. And one of the main one really is that the biggest data sets we have right now for object detection, there's a huge class imbalance between the large objects and the smaller ones. And that's all for my talk. Thank you.
Thank you, Rafael, for the presentation, insightful presentation for small object detection. Are there any questions from our listeners, from the attendees? You may send your questions in the chat. Maybe I'll start, I'll give you a question about what you have presented. Can we go back to tiling? So this is a common problem on tiling. What happens whenever there are like objects that are stuck in between two tiles? Will they get like detected or not? You're muted, Rafael.
Sorry, sir. One of the main things I see in tiling is they don't split up the image evenly. So that you see here, even though this part, this higher area already catches these cars, it's still kind of seen in the other side. So this this type of thing tries to stop that problem, sir. So it stops the problem of objects being cut in the middle by making sure your tiles go through like the area multiple times so it isn't split up perfectly.
Okay, kuha. Right, that's one probable solution for it. Pero minsan if it's a counting problem, sometimes you detect the same
Yes, sir.
objects
So that's
naman.
one of the things Sahi, the thing I showed, wants to fix also. So that's one of their main things. They try to ensure that the different patches are harmonized and that no object is detected multiple times. And it makes it it's a very accessible implementation of styling, sir.
We can easily like include it into our object detection models.
Yes, sir.
Okay, we
It's
can
like
probably try that. Thank you. There's a question here from Ian. In the Bi-FPN, on what level is the feature map still significant? Did you get the question or do you need?
Yes, sir. So here in the Bi-FPN, the feature maps are going to be significant everywhere because you see it here, right? This is the output node of the feature map. It's still going to be, since there's direct connection layers, these ones, they're still going to be significant in every iteration of the calculations kasi they're going to be connected pa. You're still not going to lose the information from the feature maps during upsampling or downsampling. So it's going to be as uh, is going to be as important as it has to be for the whole process.
So all levels of
Yes, sir.
maps are being
That's the
used.
that's like one of the main things because this isn't just based by FPN. This is one of the main things they added also because you don't want to lose this information from the feature maps.
Just curious, is there a standalone paper on Bi-FPN? Or is this, saan mo kinuha yung ano? This,
So there was a first paper for Bi-FPN, but this one builds on it kasi the first one is efficient depth, sir. This is the one I saw. Then this one builds up on the Bi-FPN by adding a shallow connection layer, sir. These ones, these
mm,
orange layers.
okay. Because I'm not too sure if there's an existing like standalone that it only introduces by FPN.
Yes, sir. They
I
use it
remember,
for models talaga. They
yeah,
have
if I
like another
remember
model.
correctly, it was integrated either in efficient net or efficient det.
Yes,
Uh,
sir.
yeah. At follow-up question from Ian. Sorry, I mean the P layers, is it only till P7? This one is as
For this specific paper, yes, they only had until P7. That's the question.
could you explain, Rafael, what it means to have what is 128 there here?
So basically so it's like the scaling of the feature maps, right? So here in the lower resolution, you're basically having it's like almost like the full image now. So 128 is basically the smaller convolutional layers because it's already starting to get it's starting to get like combined or something. It becomes smaller. So
Okay.
that's my way of understanding.
If I may, can you go back to that slide? So you have here, let's say for example, your input image, ang size niya is 512 by 512. What is this? What is the size of this feature map? This one.
What's sir?
If your input size is 512 by 512, what's the size of P1?
The same size, sir.
It
Five
would be
one
the
two
same,
five
right?
one two. Yes, sir.
How about P2?
Here you divide it, so it will be 256, sir.
256. Okay. I'm not sure about the implementation, but it seems like if this is 512, parang you are lowering the spatial resolution here already, even at P1. Probably baka in the implementation, it's still the same size. But usually, the way that I understand it, we'll have to do more reading on this. But the way that I understand this is half the size. This is quarter of the size. So parang if this is 512, then most probably it has already downscaled here to 256. Tapos dito divide 256 by half again and so on and so forth. Okay? So that's in decreasing resolution of the images. That's why this is already, if I'm not mistaken, if this is 512 by 512, this is already 4 by 4, which is already very small. So if we decreased it further, it will be smaller than 4 by 4, which sometimes might not be useful anymore. I think that's the question of Ian. But if we adjust like the input resolution, let's say to 1024 by 1024, divided by 128, right? It's a bigger image resolution. So you can still have P8 probably. It depends on the input size. But if the input size, I think, is around 600 by 600, or usually this is 512 by 512, up until here, we stop here na. Because this is already a small image or small resolution. If I'm not mistaken, 4 by 4 na siya dito. Did we answer the question, Ian? Okay, thank you. My other question, let me just read. There's another question. So this is like the model zooming in into the image to detect object based on the top-down pyramid. I think this is something to do with the tiling solution. So it's more of a comment, not really a question. Is that correct, Kate? My question before since we're waiting for Kate, could you describe, although you have already described it in the presentation, but what makes Bi-FPN better than FPN alone? What did Bi-FPN introduce to make it better?
So, sir, it makes the fusion like so in the fusion itself, it has weights now for each connection, and also adds bottom-up connections. Because here we just go top-down, right? We just upsample it. Here we have upsampling and downsampling, and each of these like output nodes have like the information from both a higher level and a lower level, sir. And there's like, since it also has each of these blocks independent, they iterate over like how a neural network would go. Then it will continue on until it finds like the most the best way to predict the
Yeah.
model, sir. And the
Mm.
best addition of this paper from the original Bi-FPN is the orange connection layer. So we don't
Okay,
lose the information from the feature map.
good. I agree. So Kate clarified. I'm looking for confirmation to check if my insight is correct. I think your insight is correct. So your model is kind of zooming in on certain part of the images to make it more,
Ah, yeah, for tiling.
yeah. So you have the right intuition. There's a follow-up question from Ian. In relation with that po, is there a reason why P1 and P2 not being included in the Bi-FPN? This is a good question. Can you answer this, Rafael? Why is P1 and P2 not in the pipeline for Bi-FPN? What?
For the pipeline here, P2 is also actually part because we see here. But
Mm,
uh,
P1, what do you think?
maybe it's since it's the full image itself already, sir.
Yeah. So what does that mean? Maybe think about the cost.
Yeah, since it's the full image, it's like it's gonna be very computationally expensive because
Yeah.
that's so much pixels pa. And it won't really help much with the actual detection because it's still like the full image. You're not really having any convolutional layer.
Yeah. You have not extracted any features
Yeah,
yet.
so there's no
Probably.
features to go, but there is for P2 here.
In relation, that is in relation with the presentation of Christian earlier. So in the early feature maps, what you have here are straight lines, very basic features, right? But the deeper networks, this is where the more complex features are present. Okay? So that's why we usually do not get information here because the information here are very quote unquote elementary. They are still very basic for us to take into account into the detection process. Okay? If you were able to, I cannot remember the talk of Carlo before, but because this is a more updated version of feature fusion. This is already, I think, 2019, 2018 paper. But if we go back to the history of object detection, this idea of extracting feature maps, so you're extracting from certain parts of the network, this stems from the idea from SSD. That's a 2015 paper. So they usually get from the last layer of the network, the middle layer of the network, tapos somewhere before or the shallower parts of the network. So the shallow parts of the network takes care of the more basic features, while the deeper parts of the network takes into account the complex features of the network. So this is the addition of the FPN. This is the contribution of FPN to make it a little bit more complex so that we can get more information. But SSD straight out, it really just gets the the feature maps no directly and use that to predict. But FPN or by FPN, it contributes this complex part in the prediction or detection. Did we answer the question, Ian? Any more questions? Those are very interesting questions that you have. This is from Efficient Debt, if I'm not mistaken. I've seen
Yes,
this
sir.
here.
But this is the paper that builds up on efficient debt, sir.
Mm. So it might be efficient net or some.
No, sir.
Maybe I'll
Uh,
have to review. Yeah. But I saw this already. So if you have no more questions, can you please raise your hand so that we can close the Q&A session for Christian? Sorry, for Rafael, rather. Thank you for the very insightful questions and also the presentation from Rafael. So I think there are no more questions. Unfortunately, we can't have the last talk on multimodal object detection because of conflict with Lazare. But we're going to have it next Saturday, hopefully. I'm going to invite everyone who signed up for this. If you're up to, if you're still okay into listening to the presentation on exploring multimodal object detection, you can join us again next Saturday. Okay? So I think that's it for this session this afternoon. Thank you again, Christian and Rafael, for presenting. Those are very insightful and good presentations that you were able to give us today. Have a great week, everyone. Ingat tayong lahat. Thank you.
Thank you, sir.
Thank you. Thank you.